Hi, welcome to tutorial number 4 of organic analysis. This is going to be a very brief tutorial on chemical tests for alcohols. So identifying that we have an alcohol used in a chemical test. It is completely something that you've seen before. It's just a quick recap because it comes up in the alcohols topic and then later comes up in organic analysis as well. So yeah, this one's going to be a very short one because in the class time I'd like to do a little bit more on infrared as well, and then your next tutorial will be on testing for other functional groups such as aldehydes and ketones, which again you've seen before, as well as alkenes and carboxylic acids. Okay, so in order to understand that you can test for different types of alcohol, you need to understand that we do have different classes of alcohol. Again, you've seen it before, it's just a recap. So I've got here 3 different alcohols, but each of them with the same molecular formula, C4H10O. So they are position isomers and chain isomers. So the first one, this is butan 1-ol. Butan because it's got 4 carbons in it, and 1 because the alcohol group is on the first carbon. Second one is butan 2-ol. And they are the only position isomers that you'll get for a straight chain alcohol with 4 carbons in it. Obviously, if you were to move this alcohol group here onto this carbon, it would still be butan 2-ol. You'd just number from right to left instead of from left to right. And finally, we have got what I'm going to call methyl propan 2-ol, or 2-methyl propan 2-ol. This methyl group, you can't actually put it anywhere else. If you put it onto carbon number 1, it would just lengthen your carbon chain and it would be a butanol rather than a propanol. If you put it on the other end, it would be a butanol rather than a propanol. So on a 3 carbon chain, you can only put the methyl group in the middle anyway, on carbon 2. So there's our 3 isomers, and they are different classes of alcohols. So the first one, butan 1-ol, if you look at the carbon atom where the alcohol group is attached and you look at what's connected to it, there is a carbon chain in one direction only. The rest are hydrogens and of course the alcohol. So this one is a primary alcohol. So look at the carbon that's attached to the alcohol group and look at how many directions have carbon chains coming off. So the second one, butan 2-ol, look at the carbon where the alcohol is coming off, and here we can see we've got a carbon chain going to the left and a carbon chain going to the right. We've got 2 carbon chains coming off this one, so this one is a secondary alcohol. And finally, the third one, there's the alcohol group, there's the carbon that it's coming off, and in 1, 2, 3 directions we have carbon chains or methyl groups. So this one is known as a tertiary alcohol. So they're your 3 different types. You need to be able to identify them. You do need to be careful, especially with things that are branch chain like this, because sometimes you get a branch chain but the alcohol is still on the end. So although it looks at glance like it might be tertiary, the alcohol itself could actually be primary, because you could end up with 2 hydrogens and the branching could be off somewhere else in the molecule. So be careful if you think something's tertiary, just double check. Okay, so one of the reactions that you looked at in the alcohols topic was oxidation of alcohols. And for oxidation of alcohols, you would use acidified, hopefully you know what I'm going to say, potassium dichromate. And if you're asked for conditions to oxidise an alcohol, you'll want to use all 3 words. You need to mention that it's acidified as well. So you look at each different classification of alcohol in turn and find out if you were to heat it with acidified potassium dichromate, what would you make? So if we look at the first one, the primary alcohol, we're going to react it with acidified potassium dichromate, which I'm going to shorten to oxidising agent, written as capital O in square brackets. You would heat it, and then you would get an aldehyde. So 1, 2, 3, 4. So you'd get the corresponding aldehyde like that. And you'd also get a water molecule left over as well. Okay, Now, with your primary alcohol, if you heat it with your acidified potassium dichromate until you get this compound here, you get the aldehyde, that's great. You can take the aldehyde and you can use that, but if you continue to heat it with your acidified potassium dichromate, the aldehyde will also then oxidize to become a carboxylic acid. So if you want the alcohol, the aldehyde, the conditions would be under distillation. So you'd have to distill it. So if you didn't distill it, if instead you heated it under reflux conditions, you would then get it to go all the way to the carboxylic acid. And again, obviously it goes via the alcohol, so it would go alcohol to aldehyde, and then it would turn into carboxylic acid. So your routes through this are either to distill it if you want to get the aldehyde, or to reflux it if you want to get the carboxylic acid. And you should know from your alcohol topic how you would set up the equipment to distill, and how you'd set up the same equipment to reflux. So you'd shift the condenser from being horizontal for distillation to upright for reflux. Okay, so on to the secondary alcohol. We've got butan-2-ol. If you were to react that with your oxidizing agent, which is acidified potassium dichromate, instead of getting the aldehyde, this time you'd get ketone, because your OH is in the middle of the compound. So if you turn that into a carbonyl in the middle of a carbon chain, it becomes a ketone. Now, once you've got the ketone, that won't oxidize any further, that can't turn into something else. So your conditions, just to make sure it goes to a completion, it's best to just reflux it to make sure that all of the alcohol turns into the ketone. Okay, and finally with your tertiary alcohol, if you take a tertiary alcohol and you heat it with acidified potassium dichromate, you would get no reaction. So tertiary alcohols cannot be oxidized by reaction with acidified potassium dichromate, because the carbon atom that's got the alcohol attached has no hydrogens attached to it directly, so you can't oxidize it. So to oxidize a tertiary alcohol, you'd have to burn it, you'd have to combust it. So even for the organic analysis section of your A-level, make sure that you know this. You should know it from learning alcohols anyway, but make sure you know how they get oxidised, what they turn into, and what conditions you'd use. Okay, so this idea of oxidising alcohols, we can use this as a test for alcohols, because there is a colour change during the reaction. So your first method for testing alcohols is oxidation with acidified potassium dichromate. So you would add some alcohol, what you will assume to be an alcohol, to acidified potassium dichromate. You would then heat that in a water bath and simply observe colour change, if there is one. So that is your first test for alcohols. If you do that, you can figure out if you've got one or not. So add some alcohol to acidified potassium dichromate, heat it in a water bath, and observe a colour change. So if we just go back to our original compounds, so these are our isomers of C4H10O, 3 different classifications of alcohol. If you were to do this method, you heat it with acidified potassium dichromate, this one would turn into an aldehyde and then onto a carboxylic acid. Your secondary alcohol would turn into a ketone, and your tertiary alcohol, there would be no reaction. And now we have a little look at the colour changes associated with these reactions. Okay, so you can see that if you have got a primary alcohol, you get a colour change. So originally your reaction mixture would look orange, so your colour change would be orange to green. So make sure if you're describing a colour change in an exam, you say what it goes from and what it goes to, not just what it turns into. So not just the second colour change. For secondary alcohol, you also get an oxidation happening. So you would see orange to green. And tertiary alcohol begins orange, stays orange. So orange, no change, because there's no oxidation reaction happening. So these colour changes come from the chromium that you're using in the acidified potassium dichromate. So the dichromate ion is Cr2O7 2-, and these dichromate ions are reduced, so they gain some electrons from the alcohol which is being oxidised, and when they're reduced they become Cr3+ ions. So dichromate Cr2O7 2- ions are orange, and chromium ions, chromium 3+ ions, are green. So you get to see a colour change. So this is a fairly good test for alcohols. It's one that's asked about quite often. One of the significant issues with it is obviously that if you've got an alcohol and you want to know if it's primary, secondary or tertiary, it can identify the tertiary one really easily by not showing a colour change. But if you've got something that you know is an alcohol and it goes orange to green, you can't be sure as to whether you've got a primary or a secondary alcohol. So you'd then have to test for something else. So if you're starting with a primary alcohol, then as you're testing it, that alcohol will be turning into an aldehyde and then onto a carboxylic acid. So you could later test for the presence of a carboxylic acid. And if you've got it, it was a primary alcohol. Your secondary alcohol, as the dichromate is turning into green chromium 3+ ions, your alcohol is also being oxidised to a ketone. So you could test for a ketone, and if you get a positive test for a ketone, then you know you began with a secondary alcohol. So we'll go through the tests for aldehydes, ketones, acids and alkenes in the next tutorial, so we save that for next week. Okay, so final little bit for this tutorial is just a second method for testing alcohols that you need to be aware of, which is by reaction with sodium. So if you take an alcohol and you drop in a piece of sodium metal, you get a reaction where you will see bubbles of gas given off. If that gas is collected and tested, it will be found to be hydrogen. So a reaction that gives off bubbles of hydrogen gas and it leaves behind a colourless solution. So here we've got ethanol, to give you an example. So reacting ethanol with sodium, you obviously get your hydrogen given off, which you'll see bubbling away. And then you also get what's called an alkoxide, or specifically sodium ethoxide. So it looks like an alcohol, mostly. So that's the start of your ethanol, but then your hydrogen comes off and you end up with that being a negative charge and sodium being a positive charge. So this is sodium ethoxide. And you can get rid of the charges and write it like this. So if we just look at balancing that equation now, we have got 2 hydrogens on the right, so we'll need 2 of your alcohols to provide those 2 hydrogens. Then we've got 2 ethyl groups, so we'll need 2 of those, and now that's given us 2 sodiums on the right, so we'll need 2 of those. So this reaction is actually very, very similar to what you've seen before with sodium, where we drop it in water. So in that case, it's actually reacting with, instead of CH3, CH2OH, it's just reacting with HOH, but it does the same sort of thing. So you take the hydrogen off to make hydrogen gas, and you stick the sodium in its place, which in this case would give you sodium hydroxide. So it's exactly the same sort of mechanism as when you put the sodium in the trough of water. You see it whizzing round and fizzing and giving off hydrogen gas and turning the solution alkaline with sodium hydroxide. Okay, so that's the second method. Works reasonably well, although sodium does fizz when you put it in lots of stuff, so it doesn't necessarily confirm without doubt that what you've got is an alcohol. You would also have to be fairly careful because, as you know, sodium would react, because it's a metal, would react with acids really well and really vigorously. So if you had any acid in there with your ethanol, you probably wouldn't want to be throwing sodium in there as well, because you'd get a fairly vigorous reaction. But it is another method that you could use for testing for alcohols, so make sure that you know those two, please. So like I said, your next tutorial is going to be on testing for the other functional groups. This was just a recap of stuff that you should already have known, possibly not the sodium part, but the rest of it should all be stuff that you've already seen before. And this is leading up to the required practical, which is testing for different functional groups using chemical tests. So this is the first part of it. So if you could now complete the post-tutorial quiz, make sure you have got your lecture notes from this mini tutorial and make sure you bring them with you to next lesson. Thank you.